Okay, so now the next question that we have is question number 5. It says 3 coins are tossed. So let's first write basically the sample space related to this experiment. So if 3 coins are tossed, did we not do this thing before? Let me see how they have solved this problem. So is it getting at least 2? It's getting at least 2 chains. No, it's okay. Now they have solved this problem a little bit differently, which is not bad. Basically that's just another way of playing with words and things like that, which is not a bad idea. So it says that 3 coins are tossed, but essentially let me explain what I mean. So if 3 coins are tossed, so the sample space for this experiment is basically you get 2 raised to the power 3, which is equal to 8 outcomes here, which is, let's say that you have HT, you have HT, and you have HT here. So you get HH, HT, you get TH, you get TT there, and then combine it with these two, you will get HHH, HHH, you will get HHT, you will get HTH, you will get HTT, you will get THH, you will get THT, you will get TTH, and you will get TTT. So you get 1, 2, 3, 4, 5, 6, 7, 8 basically outcomes here as the sample space of this experiment, which I can write as, for example, S is equal to basically HHH, and then HHT, and then HTH, and then HTT, and then THH, and then THT, and then TTH, and then TTT. So once you have your sample space, you want to describe 2 events which are mutually exclusive. 2 events that are mutually exclusive. So 2 events that are mutually exclusive would be, for example, so first of all, let's understand what is mutually exclusive. So 2 events that are mutually exclusive are basically 2 events that cannot happen together, meaning that, for example, let's say that for example, of course, any of these events, if you take them, the simple events, for example, these are you can list all the simple events over here. For example, A is equal to HHH, meaning getting 3 heads basically. or 3 heads in a row. Or for example, you can define another event as HHT, and that would be getting basically 2 heads and a tails. That would be another another event. Or you could have another event as, for example, HTH, which is another event over here, and you can just keep going like that. And each of these events are called basically simple events. Now, so now basically 2 events that are mutually exclusive, you can say that, for example, based on for example, I can take, for example, these 2 events, right? I can take, for example, this event and this event together, and you can see that these 2 events have basically 2 heads, right? So I can define an event and say that basically the event of getting 2 heads, for example, 2 heads and 1 tails. So if you take a look at, for example, if you take a look at this event, you will see that all basically the outcomes favoring this event would be only these 2 outcomes, meaning that then based on the definition of this event, you can write basically A is equal to, for example, HHT and THH. So this would be, for example, one event. Another event, and of course these are not related to anything we are doing right now. Another event that I can define here is basically, for example, B, and I can define this event as the event of getting, for example, either 3 heads or 3 tails. The event of getting, for example, either 3 heads or 3 tails. That would be another event that you could define anything, as long as you can find, as long as it helps you to demonstrate this basically this situation here. And then that would be, for example, B is equal to the event of getting either 3 heads would be HHH, or 3 heads would be, or 3 tails would be TTT. We have both of these in here, this one and this one. Now you can see that A and B are mutually exclusive because A intersection B is equal to the null set. The intersection of A and B is equal to the null set, meaning that if this is your, for example, let's say that this is your universal set, and for example A is HHT, THH, HHT and THH. This is your set A. And your set B is, for example, HHH and TTT. And let's say that these 2 sets are a part of basically a subset of the universal set in here. Now you can see that basically the intersection of A and B is basically this part over here. This is A intersection B, right? And of course A union B would be the whole thing over here. This would be A union B. This part over here, basically all of these parts over here would be including this intersection, and everything that would be A union B. Now, forgetting about A union B, which is not very relevant really here, go back here and go back a couple of steps. Okay. So now coming back here, A intersection B is, as you can see, is equal to the null set, because there is no element here that these two sets have in common. So when you have this kind of situation, what that means is that then there is no outcome that can ensure the occurrence of these two events simultaneously. Meaning that either, for example, HHT happens, either HHT occurs, in which case basically in which case event A happens, or THH occurs, in which case, okay, so we said that either HHT occurs, for example, in which case which basically ensures the occurrence of event A. Or let's say THH occurs, which ensures the occurrence of event A. And you could say that, for example, HHH occurs, which ensures the occurrence of event B. Or TTT occurs, which ensures the occurrence of event B again. Now, if you had, for example, the set A as, for example, HHT, as you have over here, and THH as you have over here, and if you had some other event, for example, over here, like for example HHH, something like this, and HHT, then basically what happens is that you can see that if HHT occurs here, that ensures the occurrence of both of these events A and C, right? So this is the kind of situation where the occurrence of one outcome ensures the occurrence of two events simultaneously. And so you can say that these two events are not mutually exclusive. These are not mutually exclusive, but these two events are actually mutually exclusive. And you can see that over here, A intersection B is equal to the null set, which means that the two events are actually mutually exclusive. So that is basically one thing that we can, that is basically the first part of this question. Now, the second part of this question is we have another problem, which is, or another question, which is three events which are mutually exclusive and exhaustive. You want to show, basically, I do need to so basically I want to show three events which are mutually exclusive. Okay, so the second part of this question is three events which are mutually exclusive and exhaustive. Which are mutually exclusive and exhaustive. Okay, so mutually exclusive and exhaustive means that basically we said that if two events are mutually exclusive, that means that basically the intersection of E of I and E of J for basically for I is not equal to j, let's say that, for example, you have all of these events like E1, E2, E3, all the way up to E of n. These are n events. These are n events related to some sampled space, for example S. These are n events related to some sampled space S. Then basically if E of I basically intersection with E of j, if this is equal to the null set for basically I not equal to j, then you say that E1, E2, E3, all the way up to E of n are basically mutually exclusive. And to be more exact, to not basically make any mistakes in notation, let me so over here we said that let me write this again. Write this part again. So in general we say that basically if E1, E2, E3 all the way up to E of n are n events of a sampled space S, and if basically the union of E of I as I goes from 1 to n is equal to your sample space here, then we call these events then E1, E2, E3 and all the way up to E of n are called exhaustive events. So this is basically the exhaustive part, meaning that when you take and of course, as you know, the union of basically E of I as I goes from 1 to n, that's the same thing as basically E1 union E2 union E3 union all the way up to basically E of n, right? So that's basically the meaning of this part, meaning that when you take the union of all of these events, that union has to give you basically the sample space, which means that basically your events basically represents the union of all of your events basically represents all the different possible outcomes of the experiment, right? So that's basically one condition here. And then if basically if E of I intersection with E of J, E of I intersection with E of J is equal to the null set for I not equal to J, for I not equal to J, that is events I, that is basically, that is events E of I and E of J are pairwise disjoint, are pairwise disjoint, then these events are called mutually exclusive events, meaning that the intersection of these events is basically the null set. They have nothing in common. Then basically you can say that E of I as E of I and E of J, etc. are mutually exclusive events. Mutually exclusive events. So that's basically the two conditions, meaning that first of all, the intersection of the events has to be the null set, and also the union of the events has to be the sample space for the events to be mutually exclusive and exhaustive, right? So now what that means is that now over here I want 3 events which are mutually exclusive and exhaustive. So what I can do, I can come in over here and pick, for example, 3 typical events. I want to pick my events in such a way that, for example, so for example, over here I have, for example, let me basically erase these. So over here you can see that I have 2 T's, 2 T's, 2 T's, and 2 T's, and so over here I have 2 T's. Over here I have 2 T's. Over here I have basically 2H, 2H, and 2H. See, over here I have 2 H's, 2 H's, and 2 H's. So now based on what I can see over here, I can basically define 2 events. The first event, I can say that A, for example, getting, for example, the event of getting basically at least 2 okay, so now if I define the event, if I define the event of getting at least 2 heads, getting at least, for example, at least 2 heads, right? Getting at least 2 heads. So that would be basically, so your A would be basically this thing over here, which is basically HHH, HHT. You would get HTH. You would get THH. And that is basically event A. Now, I can define another event as B, and I can say that, for example, event B is supposed to be, for example, this event of getting at least 2 tails. at least two tails. So the event of getting at least two tails. And what that means is that then, for example, this event B would be basically B is equal to would be basically HTT, for example, would be THT, getting two tails, THT. Then you would have TTH. Then you would have TTT. Then you would have TTT over here. So now you can see that basically now these two events A and B that we have defined here, we said that basically if we want the events to be mutually exclusive and exhaustive, basically two conditions have to be met. First of all, the union of the events has to be the sample space. And also the intersection of the two events the intersection of the events has to be the null set, or phi. So now if you check here, for example, what you can see is that if I take A union B, what I will get is basically HHH, HHT, I get HTH, I get THH, I get HTT, I get THT, I get TTH, I get TTT. And you have 1, 2, 3, 4, 5, 6, 7, 8, basically 8 outcomes here, and that is actually equal to S, which is the sample space. And A intersection B, and then A intersection B is actually equal to, so you cannot find HHH, you cannot find it here, HHT, there is no way that you can find any of these outcomes in this set or in this event, meaning that HHT, for example, it's not there, or HTH is not there, or THH is not there. So that is equal to the null set. And therefore you can say that events A and B are mutually exclusive and exhaustive. So what that means is that in this situation, that means that the event of there is basically no outcome here that can ensure the occurrence of basically these two events simultaneously, meaning that any of these outcomes that you try, that will ensure the occurrence of one of these events, either A or B, but not both of them together. So that's not possible. So that's basically one thing. And also these two events basically put together the occurrence of both of these events, that means that basically that represents all of the different outcomes of this experiment. And that's basically that's basically called the exhaustive part. And what I talked about previously, that is the mutually exclusive part. Okay, so that is now this part. And then the next part of this question is the next part of this question is okay, so let's see. So we are looking for two events which are not mutually exclusive. Basically, we are looking for two events which are not mutually exclusive. So two events which are not mutually exclusive would be, for example, let's suppose that, for example, let's define an event here, for example, an event A. I'm going to define as, for example, getting basically one head on the first try, or getting a heads on the first try. So getting a heads on the first try would be, for example, A would be equal to basically HHH, then you would have HHT, then you would have HTH, then you would have HTT, then you would have, and that's it, right? So that's getting a head on the first try. You have all of these H's on the first try. Now I can define another event as, for example, B, and for example over here I'm going to define getting at least, for example, getting at least two heads. The event of getting at least two heads. So the event of getting at least two heads would be basically, for example, HHH. You have HHT. You have HTH. You have HTT. You have THH. You have THH. You have, and that's it. Now, as you can see, basically then A intersection B is equal to, well, HHH, then you have HHT, then you have HTH, then you have HTT. So, and that means that A intersection B is not equal to the null set. And so you can say that A and B, the events are not mutually exclusive. Are not mutually exclusive. So that is that. And the next part of this question would be two events which are mutually exclusive but not exhaustive. Okay. Okay, so the next part of this question is you're looking for two events which are mutually exclusive but not exhaustive. So two events which are mutually exclusive, two events which are mutually exclusive but not exhaustive. But not exhaustive. So for example, if I define for example some event over here, for example event A, and if I say that to get basically ahead on the first try, for example, to get ahead, the event of getting ahead on the first try. So the event of getting ahead on the first try would be basically HHH, HHT, HTH, HTT. These are all outcomes that would basically favor this event of getting ahead on the first try. HHH, HHT, HTH, and HTT. Now I'm going to define another event. I'm going to define another event as B, and I'm going to call it getting a tails on the first try. Getting basically a tails. This is also heads. Tails on the first try. But not, for example, but not 3 heads in a row. But not 3 heads in a row. So getting 3 heads on the first try, but not 3 heads in a row. That would basically be all of these. I keep forgetting this word. All of these. All of these. THT. And THH and THH and TTH, but here we said that but not 3 heads in a row. Not 3 heads in a row would be basically would exclude this one. So now of course basically A intersection B is equal to the null set, meaning that there is no members here, meaning that the A and B have no members in common, or no, I keep forgetting that word. Anyway, there is nothing that they have in common. So A intersection B is the null set. And also, as you can see, if I calculate A union B, that would give me HHH and HHT and HTH and HTT and THT and THT and THH and TTH and TTH, and that's it. So I have 1, 2, 3, 4, 5, 6, 7, which means that this is not equal to the sample space. Which means that this is not equal to the sample space. So what that means is that, of course, these events, these two events A and B, are, of course, mutually exclusive because their intersection is the null set. So A and B are mutually exclusive, but not exhaustive, because basically A union B is not equal to S. So that's basically, for example, two events that you can basically define this way to basically to show two events which are mutually exclusive but not exhaustive. Now the next thing that we have here is three events which are mutually exclusive but not exhaustive. Okay, so basically let's do it. Let's start from here. So instead of two events, now we are going for three events. Okay. Okay, so now three events which are mutually exclusive but not exhaustive. So mutually exclusive meaning that, for example, you could say that for example, event A, you could define an event A saying that, for example, getting three heads in a row. So for example, getting three heads in a row, which would be basically A is equal to HHH. B would be, for example, you could say getting, for example, getting the event of getting, for example, three tails in a row. Which would be basically B is equal to T T. And the event C, I define it as, for example, getting one head, for example, or getting one tail. The event of getting, for example, one tails. The event of getting one tails would be, for example, this one and this one and this one, and that's it. So HHT, HTH, THH. So of course we can see that these events are mutually exclusive, meaning that are pairwise mutually exclusive, meaning that A intersection B is equal to the null set, A intersection C is equal to the null set, and of course you know that A intersection B is the same thing as B intersection A. The order doesn't really matter in the algebra of sets. A intersection B is actually equal to B intersection A. And so A intersection B and A intersection C is equal to the null set. Now B intersection C is also equal to the null set. So these are all the distinct pairs that you can make with these three sets as far as the intersection operation is concerned. Otherwise, for example, you could also write B intersection A, which is the same thing as A intersection B. So for the same reason, basically writing A intersection B is enough. You don't have to write B intersection A, because that's basically the same thing. So what that means is that, so A intersection B, A intersection C, and B intersection C, and that's it. So that means that basically you can say that the three events A, B, and C are mutually exclusive, right? But if you write basically A union B union C, what you would get is basically HHH, you would get TTT, you would get HHT, you would get HTH, you would get THH, and that is of course not equal to S. That means that, and therefore you can say that the three events A, B, and C are not exhaustive. And that's the end of basically question number 5. Now question number 6 is two dice are thrown. The events A, B, and C are as follows. And describe the events Okay, so let's go step by step. So 2 dice are thrown. 2 dice are thrown. That means that so basically in the case of basically 2 dice, you would have basically all of these different I keep forgetting that word. Outcome. You have all of these outcomes, meaning that call this, for example, dice 1, and call this, for example, dice 2, and you have 1, 2, 3, 4, 5, and 6 here, and you have 1, 2, 3, 4, 5, and 6 here, and here you have dice 2. We call this dice 2, for example. Let's call this dice 2, dice 1, and dice 2. So then you would get, for example, 1, 1, you would get 1, 2, you would have 1, 3, and all the way up to 1, 6. Over here you would get 6, 1, and all the way up to 6,6. So, and you have basically in total you have 36 outcomes. 36 outcomes. So the event of getting an even number on the first dice, the event of A basically is getting an even number on the first dice. Which would be basically getting an even number on the first dice. You would have to go with basically 2 and 4 and 6, and you would have basically all of these outcomes as A is equal to, for example, 2, 1, 2, 2, all the way up to 2, 6, and then you have 4, 1 and 4, 2, all the way up to 4, 6, and then you would have 6, 1 and 6, 2, all the way up to 6, 6. Okay, so these are basically the outcomes that would favor basically event A. Now event B would be getting an odd number on the first dice. Event B would be getting an odd number on the first dice. Which would be basically B is equal to, basically odd numbers would be 1 and 3 and 5. So you would get 1, 1, 1, 2, all the way up to 1, 6, and then you have 3, 1 and 3, 2, all the way up to 3, 6, and then you would have basically 5, 1, 5, 2, all the way up to 5, 6. So that would be event B. Now event C is getting the sum of the numbers on the dice less than or equal to 5. Event C is getting the sum of the numbers on the dice, getting the sum of the numbers on the dice is less than or equal to 5, which means that less than or equal to 5 would be 1, 1 through 1, 4, right? So you would get basically C is equal to 1, 1 and 1, 2, all the way through 1, 4, which would be 5, and then you would have 2, 1 all the way through 2, 3, which is 5, 2, 1, 2, 2, all the way through 2, well, there is no need to write it that way, and 2, 3, and then you have and then you have 3, 1 and 3, 2, 3, 1 and 3, 2, and then you have 4, 1, 4 comma 1, and then 5 comma 1 would be 6. So it has to be less than or equal to 5. That's basically all that you get here. So what that means is that then these are the events that we have. Now we want to describe the event, for example, the event A prime. We want to describe the event A prime, which is nothing but the complement of A, which is nothing but the complement of A. And as you can hopefully remember, the complement of A is basically relative to some universal set, meaning that you have some universal set over here. And let's say that you have, for example, the set A, for example, 1, 2, 3, 4, and 5. And these are the members of set A. And you have basically 6, 7, 8, and 9. And you have a 10 over here as well. And these are the members of the set B, right? And this is the universal set, which we call U. And of course you can see that basically in this and this is called a Venn diagram, if I have written that properly. A Venn diagram. Yes, this is called the Venn diagram. So now on a Venn diagram, we can basically see all of these very clearly, meaning that, for example, the set A would be, set A over here is, if you wanted to write it in set notation, would be 1, 2, 3, 4, 5, 10. 1, 2, 3, 4, 5, and 10. Set B would be 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, and 10. 5, 6, 7, 8, 9, and 10. Now A intersection B would be basically what A and B have in common, which is 5 and 10. And A union B is the same thing as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? Now, for example, A minus B in this demonstration, A minus B is the same thing as 1, 2, 3, 4. 1, 2, 3, and 4. B minus A is the same thing as 6, 7, 8, 9. 6, 7, 8, 9. And basically A prime or the complement of A is the same thing as basically 6, 7, 8, 9 again. 6, 7, 8, 9. Meaning that all the members of, this is all the members of, all the elements of U except for the elements of A. And also B prime, which is the same thing as A complement or complement of A, is, well, just simply you can also call this, not A as well. You can call this not A as well. Not A. Now this you can call not B as well, right? Not B. So that means that you have basically, you will get B prime or B this is actually supposed to be B complement. So you get all the members of U except for the members of B, which is 1, 2, 3, 4. 1, 2, 3, and 4. So this is all the members of all the elements of U except for the elements of B. So now we know what these are. Now there is something over here that I'm not really sure about, and that is B or C, A or B. Okay, those are the kinds of things that have not much to do with sets. We need to go back and do a quick review on what we on the theory that we did on probability, and then we'll come back here and solve this problem. Okay, so now there are a few things over here that we need to go back and review. So I suppose, I'm not really sure, because I have conflicting information from different sources in my mind. We will have to confirm all of these, but I suppose there are basically two things over here. One of them is A prime, and one of them has been written as, for example, not B. So I think that A prime and not B, meaning that if you write not B, that would be the same thing as B prime. But I'm not really sure about this. We'll have to look this up, see what that is. Now there is something called A or B, for example. There is something called A or B. And there is something called A and B. That basically there is or and here. We need to look this up as well. There is something called A but not C, for example. A but not C. We'll have to look this up as well. And there is and again and or again. So these are then again the same, basically another problem. So let's start with these two, and then we will get to the rest of the things. Now, in order to confirm this, we need to take a look at the answers, because there is no way to look this up. There is no way in the text that we can confirm this. But so, meaning that, of course, these are not related to this problem over here. So I will just simply erase them. So we have basically C over here. I can erase it over here. And what we want to know is that if not B is the same thing as B prime. If I want to know, for instance, if not B is the same thing as B prime, which is, I suppose this must be the complement of B, and this must be again in this context, at least the complement of B. Let's see if they are the same things. So now the first question that we have here is that we want to describe these events, the event A prime. So I suppose if that's the case, then I could write this as for example not A, and not A would be getting an even number on the first dice. Let me see how they have solved the problem. I don't want to basically spend. So this is question number 6. What is this thing? 16.2. Number 6. Okay. So it says that 2 dice are thrown. The events A, B, and C are as follows: getting an even number on the first dice, getting an odd number on the first dice, and getting the sum of the first of the numbers on the dice is less than or equal to 5. And then describe these events based on these events over here. So you have basically when 2 dice are thrown, the sample space is given by this. S is equal to all the ordered pairs x comma y, such that x comma y is equal to 1, 2, 3 through 6. So accordingly, A is equal to basically this set, B is equal to this set, and C is equal to this set. And so A prime is the same thing as you can see, A prime is the same thing as B. And what is B here? Okay, so that means that this is not A. So here I have basically getting an even number on the first dice. So then that would be basically all of these outcomes here. And so A prime, which is, I suppose, let me go into the text and see what we have here. I suppose we had something. Let's see. Now there is some material here. So let's go through the material that we have here. I think the answer can all be found right here. We don't really need to go anywhere else. So we have or, and, but not, right? Or, we are looking for or, for and, for but not, and we are looking for not, for example, A, which is something like, for example, must be something like A prime. Let's see what that is. So it says that for basically in the part that we did about the algebra of events. So let me actually end this video here, and we will continue with the rest of this in the next video.